All right, so we're back. We're going to talk now about our last type of electron configurations, right? We've talked about our normal electron configurations. We've talked about the orbital notation, the abbreviated electron configurations, and then also we talked about Bohr diagram configurations, but we're going to kind of ignore those. Now, our last type of electron configuration are the Lewis dot diagrams, okay? And this only illustrates the valence electrons. So if we remember valence electrons, our valence electrons are the electrons that are in our highest energy level. Okay, so oftentimes in chemistry, right, a lot of our chemistry that happens, right, our chemical reactions, things that change, we see these changes because of changes with the valence electrons. Okay, so the outermost electrons, right, all of our electrons essentially have no mass, and so they're able to move around really easily. They are involved in bonding, they're involved in chemical changes. Oftentimes, right, we are going to see the movement of some of these electrons. So the movement of those electrons, okay, the changes that we can perceive, these happen due to changes with the valence electrons, right? These are the outermost electrons. They're the furthest away from the nucleus, so they're going to be able to move around the easiest, all right? So that's why we use our Lewis dot diagrams, right? So we're going to write the element symbol, add the s and the p electrons from the highest energy level, okay? And then we use our dot representation, okay? So we're going to do two different examples here. One of them, I'm going to do carbon, right? So if I were to write the carbon electron configuration, I would say 1s2, 2s2, 2p2, okay? So I have 4 electrons that are in the second energy level, right? This is the second energy level, this is the second energy level. That means that both of these electrons, or all 4 of those electrons, are in the highest energy level. Those are my valence electrons. So now I can take my element symbol, and I can take my 2 electrons in the 2s and my 2 electrons in the 2p, and put them onto my carbon, right? I'm going to put them 1, 2, 3, 4, right? There are 4 spots that I can put my dots for my carbon atom, okay? And I'm going to put them above, below, to the right, and to the left. Each dot now represents an electron. I can either do the 4 all spread out like this, or I can kind of show that 2 of them are in an s orbital there by going carbon here with 1, 2, and then 1 electron and 1 electron, okay? So again, our valence electrons are the electrons that are in the highest energy level, okay? So I'm going to take, and we're going to go down to the bottom here, and we're going to do another example. If we do another example here, what I'm going to do is bromine, all right? So bromine, of course, a bromine atom would have 35 electrons. And if I were to write my abbreviated electron configuration, I'm going to start from argon, the previous noble gas, right? It's got a noble gas or argon configuration, and then I'm going to start filling in. I have the 4s2, the 3d10, and then the 4p5. So my valence electrons are my electrons in the 4th energy level. Okay, the 3d10, right? The 3d10 electrons, we say that this orbital here is higher in energy than the s orbital. But in reality, it gets more complicated than that. So we kind of can ignore that and say, okay, these are lower energy level, right? This is a lower energy level. 3 is lower than 4. So the 4th energy level is my highest energy level. These 7 electrons are in my highest energy level. Okay, so my Lewis dot diagram for it would be 1, 2, 3, 4, 5, 6, 7 electrons. Okay, I have 7 dots around my bromine symbol, so I have 7 electrons that are in the highest energy level. 4s, 2, 4p, 5. 2 plus 5 is my 7 electrons. Okay? Now let's talk about if we have an ion. If we have an ion, we are going to look at S minus 2. So sulfur with a minus 2 charge, we're going to add 2 electrons to the 6 that the sulfur, normally has in its valence shell. So if I wrote the sulfur configuration normally, right, it would be neon, and then 3s2, 3p4. That would be my 6 normally, but I have 2 extra. So now my 3p is going to be 6. So that's 2 plus 6, that's 8 electrons. So I can put my sulfur around, right? 1, 2, 3, 4, 5, 6. That would have been my normal configuration, but with the minus 2 charge, I've got 2 extra electrons. Now I have 8 dots around my sulfur. So oftentimes, right, most of our ions, they're always generally going to end up with 8 electrons around them, right? 8 dots, 8 electrons. The reason being that having that full valence shell is generally more stable, okay? So we have a full valence shell. We can't fit any more electrons into the third energy level here unless we go to our 3d orbital, okay? So we have a full valence shell, so this is a more stable, is a very stable ion, okay? So that was with our anions. With our cations, we're going to subtract, right? Subtract 1 electron from the valence shell of potassium. So potassium normally, right, would have an argon configuration and then would add 1 electron, right, our 4s1. But we're going to remove 1 electron. So that means that we now have an argon configuration. So I would write K, and I could either write without any dots, or, right, now my argon configuration, my highest energy level, my valence electrons, are now the 3s2, 3p6. That 8 electrons, I can draw my 8 electrons around that as well. Okay? Either one of these works. So again, our ions always end up with 8 electrons. Okay? Generally, that works. Some of our transition metals, it starts getting more complicated, but we're not going to test you on that. Okay? So that's our Lewis dot diagrams.